So in this video, I will give you a short introduction of the Schrödinger equation in quantum mechanics. So first of all, imagine that we have a particle of a mass m, for example, an electron, which is moving in a free space with a velocity v and is subject to some specific force F. And let's assume that the force is a function of the position and the time, and also the velocity, which is function of the position and time, which R so is the position vector, which is given in this coordinate Cartesian system by x u plus y g plus z k. So in classical mechanics, what we aim to determine is the position vector at a given time t, or in other words, the trajectory of our particle at a given time t, and this mean is to give the x position at a given time t, the y coordinate at a given time t, and the z coordinate at a definite time t. So once we know that, so this quantity, we can determine the velocity of our particle, which is defined as the derivative of the position with respect to the time. We can also determine the momentum of our particle, which is defined by the mass times the velocity. So here is the velocity. And moreover, we can determine also the kinetic energy, which is defined by 1/2 mv squared. And this what we can do in classical mechanics, okay? So the question is how to determine this quantity, the position of our particle at a given time t. And simply we apply the Newton's second law, which is given by the force, which is equal to the mass times A, with A is the acceleration of our particle and is defined as the derivative of the velocity with respect to the time, which is equal also to the second derivative of the position with respect to the time. So in the case of a conservative system, which is the only kind of systems that occur at the microscopic level, so we can express the force F as a derivative of a potential energy function, noted, for example, V capital letter of X, so this is the potential energy function of our particle. And we can, so here, let's assume that our particle move only along the X direction, and to simplify the calculation, and let's assume that, so this is our particle which moves only along the X direction. and the R is equal to x times E. So we can express the force as, so F, which is equal to the minus the derivative of the potential V with respect to the coordinate X. So this for the specific case, for the specific case of a conservative system. Then we can express the Newton's second law as follows. So it is very simple to demonstrate that this this relation can be expressed as follows. So we have the mass by the second derivative of the x with respect to the time was equal to the minus the derivative of the potential V with respect to the x dimension. So now in classical mechanics, so from this relation together with appropriate initial conditions, and typically the position and the velocity at t equals 0. So this would, let's note it, R0 and V0. The position vector and the velocity at t equals 0. So with this initial conditions and this relation, we can determine the trajectory of our particle at a given time t. Okay? Now, in quantum mechanics, so the quantum mechanics approaches the same problem quite differently. So the quantum mechanics, in quantum mechanics, what we are looking for is what we call it the wave function. The wave function, noted by psi of x and t. And this function characterizes the quantum state of our particle. And we get this function by solving the Schrödinger equation. And the Schrödinger equation is given by this expression. So we have E h bar, the derivative of psi with respect to the time, which is equal to the minus h bar by 2m over 2m multiplied by the second derivative of psi with respect to the x dimension plus the potential V by the psi function. So here the h bar is the Planck's constant divided by 2 pi, which is equal to 1.54 or 10 minus 334 joule by second. So to resume, in classical mechanics and quantum mechanics. So in classical mechanics, we aim to determine the trajectory of our particle by using the Newton second law, F equal to m time the acceleration, and this relation with the initial, so appropriate initial conditions, which are R0 and V0 at t equals 0, and the Schrödinger equation in quantum mechanics play a role logically analogous to the Newton's second law, given suitable initial conditions, and typically we use the wave function at t equal 0, and using the Schrödinger equation, we can determine the psi of x and t for all future time, just as in classical mechanics, Newton laws determines the position at a given time t for all future time.